Welcome to the world of web applications, a world that powers nearly everything we interact with online. From social networks and e-commerce stores to email platforms and cloud-based tools, web applications are the digital engines that make the internet dynamic and interactive. In this video, we're going to take a deep dive into the basics of web applications, walking through all the core components you need to understand how they work, how they communicate, and how they stay secure. Whether you're just starting your journey into web development or you're curious about how the internet functions behind the scenes, this is the perfect place to begin. Let's start with a creative analogy. Imagine a web application as a planet. Just as astronauts land and explore only the surface of a planet, users only interact with the visible parts of a web application through their browser. Beneath its surface, however, lies a complex structure, layers of infrastructure, data handling, and security protocols that keep everything functional. In the case of a planet, there may be tectonic plates, underground tunnels, and natural forces that affect life on the surface. Similarly, in a web application, the visible interface is only a fraction of the whole system. Let's now break down what lies on the surface and what powers it beneath. The front end is the part of a web application that users see and interact with. Think of it as the surface of the planet, the land, sky, and vegetation that astronauts can observe. In technical terms, the front end is made up of three core technologies: HTML, CSS, and JavaScript. HTML, or hypertext markup language, forms the backbone of any web page. It provides the structure and layout of content. Imagine simple organisms on the planet whose DNA holds instructions for their basic form. HTML serves a similar purpose. It doesn't handle styling or logic but tells the browser what to show and in what order, like where the headings, paragraphs, buttons, and images go. CSS, or cascading style sheets, takes that basic structure and gives it personality. It defines the appearance of the HTML elements, the colors, fonts, spacing, and overall layout. If HTML is the DNA, CSS is the genetic expression that determines an organism's size, shape, and skin color. It allows developers to make web applications look modern, clean, and user-friendly. JavaScript, or JS, is where the real magic begins. It introduces interactivity and dynamic behavior. Unlike HTML and CSS, which are static, JavaScript enables things like clicking buttons, submitting forms, opening menus, or changing elements without reloading the page. In our planetary analogy, if HTML is the body and CSS is the style, JavaScript is the brain. It lets the application think, react, and make decisions in response to user actions. The back end. Now let's go underground, to the back end of a web application. This is the part you don't see when visiting a website, but it's absolutely essential for everything to work. On a planet, this would be like the internal ecosystem, gravity, atmosphere, and infrastructure that support life on the surface. One of the most important components in the back end is the database. This is where all the information is stored. Think of it as a library, a filing cabinet, or a digital diary. Whenever you log in, post a comment, or change your settings, that information is written to or read from a database. It's how web applications remember you and serve personalized content. Then there's the infrastructure, a vast array of components that allow the application to function smoothly. This includes web servers, which serve up content, application servers, which process logic and computations, storage devices that keep files, and networking hardware that connects it all together. Imagine the roads and highways on our imaginary planet, the cars that travel on them, and the fuel that powers everything. That's what the infrastructure does for a web application. Finally, we have the web application firewall, or WAF. This is like the protective atmosphere of a planet, shielding its inhabitants from harmful cosmic rays. In the web world, WAF protects applications from malicious requests and cyber attacks. It filters traffic, blocks threats, and acts as a first line of defense against intruders. Uniform Resource Locator, URL. When you access a website, you type in a Uniform Resource Locator, or URL. This is the web address that helps your browser find and connect to online content, whether it's a web page, image, or video. But a URL isn't just a random string of characters. It's made up of several key components, each of which plays a role in guiding your browser to the correct destination. The scheme is the first part of a URL, like http:// or https://. It tells the browser what protocol to use. HTTPS is more secure because it encrypts the data being sent, which is why modern websites prioritize it. Sometimes, URLs include a user section, which may hold login details like usernames. While this was more common in the past, it's now considered risky because exposing credentials in a URL can lead to serious security issues. Next comes the host or domain, which specifies the actual website address, like example.com. Every domain name is unique and registered through domain authorities. Be cautious of domain names that look similar to real ones but have small, tricky changes. This is called typo squatting and is often used in phishing attacks. The port tells the browser which doorway to use when connecting to the server. Most common ports are 80 for HTTP and 443 for HTTPS. Unless specified otherwise, your browser picks the default port based on the scheme. The path in the URL is like a file trail, it points to a specific page or resource on the web server. For example, /product/shoes might take you to the shoe section of an online store. After the path comes the query string, which begins with a question mark. This is used to pass data, like search terms or form entries. Because users can modify this data, it's important for developers to secure it to prevent attacks like injection, where malicious input is sent to break or exploit the system. Lastly, the fragment, which begins with a hash symbol, hash, lets users jump to a specific section of a page, such as a table or header. Like query strings, fragments should be handled with care to avoid misuse or security problems. HTTP messages. Let's now explore how communication happens between a user's browser and the web server. This is done using HTTP messages. Every interaction, from loading a page to submitting a form, involves sending and receiving these messages. There are two types, HTTP requests and HTTP responses. An HTTP request is what the client, your browser, sends to the server, asking it to do something, like load a web page or submit form data. The HTTP response is what the server sends back, providing the requested content or reporting an error. Each HTTP message has 4 parts. The start line introduces the message. It specifies whether it's a request or response and gives key instructions. Then come the headers, which are pairs of information about the message, like what kind of data is being sent, what browser is being used, or when the message was created. The empty line is a simple divider between headers and the main content. And finally, the body contains the actual data being transferred. This might be HTML, user input, or API content. Understanding HTTP messages is essential because they form the foundation of web communication. They help diagnose problems, improve performance, and play a critical role in cybersecurity. A poorly structured message can create confusion or vulnerabilities, so getting this right is key to building strong, secure applications. Now that we understand the structure of HTTP messages, let's break down an actual HTTP request, starting with the request line. This is the very first line in the message, and it tells the server what the client wants to do. It includes 3 elements, the method, the URL path, and the HTTP version. For example, in get/login HTTP/1.1, the method is get, the path is /login, and the HTTP version is 1.1. Each of these plays a unique role in helping the server understand what the client is trying to achieve. Let's talk about the most common HTTP methods. Get is used to request data from the server without making any changes. It's safe and fast, but shouldn't be used for sending sensitive data like passwords, since everything sent in a GET request appears in the URL. Post sends data to the server, typically when submitting forms or creating something new. Because data is sent in the body, it's more secure than GET, but still needs proper validation to prevent attacks like SQL injection or XSS. Put replaces or updates an existing resource. It's often used in RESTful APIs when modifying entire data objects. Delete removes a resource. Just like put, it should be protected to ensure only authorized users can delete data. Less common but still important are methods like patch, which updates just part of a resource, head, which retrieves only the headers without the body, and options, which reveals what methods a resource supports. There are also trace and connect, used for diagnostics and encrypted connections respectively. Some of these methods are disabled on servers by default due to potential security risks. Next is the URL path, which points to the exact resource the user is trying to access. In the URL https://example.com/API/users/123, the path API/users/123 identifies a specific user profile. This part of the request is often targeted by attackers trying to manipulate or access unauthorized data. That's why it's important to validate paths, restrict access, and sanitize inputs. The HTTP version specifies which version of the protocol is being used. Let's go over a few. HTTP/0.9 was the earliest and only supported GET. HTTP/1.0 introduced headers and basic caching. HTTP/1.1 brought persistent connections, chunk data transfers, and remains widely used today. HTTP/2 added performance upgrades like multiplexing, header compression, and prioritization. HTTP/3 is built on quick and offers faster, more secure connections with minimal latency. Though HTTP/2 and HTTP/3 are faster and more secure, many websites still operate on HTTP/1.1 due to widespread compatibility. Let's now look at request headers, additional pieces of information sent along with the HTTP request. These are structured as key value pairs and help both client and server understand each other better. Some common request headers include: host, specifies which domain the client is requesting, like host, google.com. User agent, describes the client device and browser, such as Mozilla/5.0. This helps servers tailor content or behavior. Refer, tells the server where the request came from, useful for analytics and security. Cookie, carries stored data like login sessions and user preferences. Content type, tells the server what kind of data is being sent in the request body, such as JSON, XML, or form data. In post and put requests, the request body is crucial. This is where actual data gets sent to the server for processing. Depending on the application, the format might differ. Common body formats include URL encoded, structured as key value pairs, like username equals admin and password equals 1234. Form data, used when uploading files or images. It allows multiple pieces of data to be sent in blocks. JSON, a lightweight format that uses name-value pairs, perfect for APIs and readable by both humans and machines. XML, a tag-based format where data is enclosed in labels, more verbose but highly structured. Every one of these formats requires strong input validation to protect against malicious data, especially for user-generated input. Once the server processes the request, it sends back an HTTP response, which starts with a status line. This includes the HTTP version, a status code, and a reason phrase that briefly describes the result. Here are the 5 categories of status codes: 100 to 199, informational, a signal that the request is being processed. 200 to 299, success, everything worked, the server is sending back the requested data. 300 to 399, redirection, the client should go somewhere else to find the resource. 400 to 499, client errors, something was wrong with the request, like a 404 not found. 500 to 599, server errors, the server failed to fulfill a valid request due to internal problems. Some common status codes include: 100, continue, the server received part of the request and is ready for more. 404, not found, the resource doesn't exist at the specified path. 500, internal server error, a generic error on the server's side. In addition to the status code, HTTP responses include response headers, metadata that helps the client interpret and manage the response. Essential headers include: date, the timestamp when the response was generated. Content type, indicates the media type, like text/HTML or application/JSON. Server, shows which software the server is using. While useful for debugging, it can expose system info and is often hidden for security reasons. Other common headers are: set cookie, sends cookies to be stored by the browser. For safety, they should be marked with HTTP only and secure. Cache control, manages how the browser stores content, either to improve speed or prevent storing sensitive data. Location, used in redirection responses to show the new address. Developers must validate this header to avoid open redirect vulnerabilities. The response body contains the actual content, HTML, JSON, or files, that the server sends back. Before returning user-generated content, it must be properly sanitized and encoded to avoid cross-site scripting, XSS, or other injection-based attacks. Finally, let's talk about security headers, a vital part of securing web applications from common threats like XSS, clickjacking, and data leaks. These headers are often invisible to users but play a key role in your browser's behavior. The Content Security Policy, CSP, header tells the browser which sources are allowed for scripts, styles, and other content. For example, a CSP like default src self only allows content from the same domain. This minimizes the risk of attackers loading malicious content from outside. The Strict Transport Security, HSTS, header forces browsers to connect only over HTTPS. This ensures encrypted communication and prevents attackers from downgrading the connection to an insecure one. You'll often see directives like max age equals 6307200 and include subdomains to apply the rule across all pages. The X content type options header prevents browsers from guessing file types. A value like no-sniff ensures the browser sticks to the declared content type, which avoids executing malicious files by mistake. Lastly, the referrer policy header controls how much referrer information is shared when a user clicks a link. Settings like no referrer, same origin, or strict origin when cross-origin offer increasing levels of privacy, ensuring users don't unknowingly expose sensitive browsing info. And that brings us to the end of our comprehensive introduction to web application basics. We've covered everything from the surface-level user interface to the deep structures of data handling, communication, and security that support modern web apps. You now understand how URLs are built, how HTTP messages work, and how important headers protect the integrity and privacy of online interactions. That's all for today. Stay anonymous, stay curious, and keep learning.